For thousands of years, humans have gazed at these stars and wondered about their size, their brightness, and their place in the cosmos. But few of us stop to ask the most extreme questions. What is the heaviest star that can possibly exist? And what is the lightest star that can even be called a star? These two opposite ends of the stellar scale are not just oddities of nature. They are the keys that unlock the fundamental rules of how stars are born, how they live, and how they die. They shape the galaxies we live in, forge the elements that make up our bodies, and set the stage for every possible world that could harbor life. Today, we are going to journey to the farthest corners of the universe to meet these record-breaking stars, uncover the science behind their extreme masses, and understand why they matter to every single one of us. This is the story of the heaviest and lightest stars in the known universe. Let us start with the upper limit, the heaviest stars. For decades, astronomers thought there was a hard cap on how massive a star could be. Early calculations suggested that no star could exceed 150 times the mass of our Sun. The reasoning was simple. A star more massive than that would generate so much energy from fusion that its own radiation pressure would blow away its outer layers before it could fully form. It was a cosmic speed limit, a line that nature could not cross. But then, in the early 2000s, astronomers made a discovery that shattered this long-held belief. Deep inside the Tarantula Nebula, a vast stellar nursery in the Large Magellanic Cloud, a satellite galaxy of our Milky Way, some 165,000 light-years from Earth, they found a star that defied all expectations. Its name is R136A1, and it is the heaviest star ever discovered by human science. R136A1 is not just a little bigger than the Sun. It is a cosmic giant. Current measurements put its mass at around 265 times that of our Sun. To put that in perspective, if you could weigh this star, it would be equal to 265 of our suns combined. Its size is equally staggering. It is about 35 times the radius of the Sun, and its surface temperature is over 50,000 Kelvin, nearly 9 times hotter than the Sun's surface. This extreme heat makes it burn with a brightness that is almost impossible to comprehend. R136A1 shines with a light of 8.7 million suns. If we could replace our Sun with R136A1, the Earth would be incinerated in an instant, and even the outer planets, like Neptune, would be blasted with deadly radiation and heat. This star is a powerhouse, a cosmic furnace that runs at full throttle from the moment it is born. But there is a cruel trade-off for being the heaviest star in the universe, a tragically short life. Our Sun will live for about 10 billion years, slowly and steadily, fusing hydrogen into helium. But R136A1 burns through its nuclear fuel at an insane rate. It is so massive that gravity crushes its core with unimaginable force, speeding up fusion to a level that is unsustainable. Astronomers estimate that R136A1 is only about 1.5 million years old, an infant in cosmic terms, and it will live for just 2 to 3 million years total. In the blink of a cosmic eye, it will exhaust its core fuel, collapse in on itself, and explode as a hypernova, one of the most powerful explosions in the universe. This explosion will not just end the star's life. It will scatter heavy elements like gold, platinum, and uranium across the surrounding nebula, seeding future generations of stars and planets with the building blocks of life. R136A1 is a short-lived hero, a star that lives fast and dies young, but leaves a lasting legacy for the cosmos. What makes R136A1 even more fascinating is how it formed. It was born in a dense cluster of stars called R136, a region where gas and dust are compressed to extreme densities by gravity and the pressure of nearby stars. In these ultra-dense nurseries, stars can pull in far more material than they can in quieter regions of space, allowing them to grow to masses that were once thought impossible. Astronomers now think that the old 150 solar mass limit was wrong, and that stars up to 300 times the Sun's mass could exist in the right conditions. R136A1 is proof that the universe is far more creative and extreme than we ever imagined, pushing the boundaries of physics to create stars that defy our earlier models. Now, let us travel to the opposite end of the spectrum, the lightest stars. If the heaviest stars are the muscle-bound giants of the cosmos, the lightest stars are the tiny, quiet runners that outlast everyone else. To understand the lightest star, we first need to know the line between a star and a failed star. A star is defined as an object that can sustain hydrogen fusion in its core. This is the process that powers all true stars and makes them shine. If an object is too small, it never gets hot enough or dense enough in its core to ignite hydrogen fusion. These objects are called brown dwarfs, often nicknamed failed stars. They are bigger than planets, but smaller than stars, floating through space as dark, cool orbs that emit almost no visible light. The critical mass boundary between a brown dwarf and a true star is 0.08 times the mass of the Sunday. That is, 8% of the Sun's mass, or about 80 times the mass of Jupiter. Any object above this line can ignite hydrogen fusion and become a star. Anything below it is a brown dwarf. So the lightest true stars are the ones that sit just above this 0.08 solar mass line, barely crossing the threshold to earn the title of star. The smallest and lightest known star that fits this description is Ogle Tree 122b, a tiny red dwarf star. Located about 1,000 light-years from Earth in the direction of the Carina constellation. Ogle Tree 122b is a cosmic minnow. It has a mass of just 0.081 solar masses only, barely above the brown dwarf limit. Its size is equally tiny. It is only about 16% larger than Jupiter, making it smaller than some of the largest gas giant planets in the universe. If you stood on a planet orbiting this star, it would look like a dim red pinprick in the sky, far smaller and fainter than our Sunday. Its surface temperature is a cool 2200 Kelvin, giving it a deep red color that is nothing like the bright yellow of our Sunday. It is so dim that it emits almost 99% less light than the Sun, making it hard to detect, even with powerful telescopes. But what this tiny star lacks in size and brightness, it makes up for in longevity. While the heavyweight R136A1 dies after just a few million years, Ogle Tree 122b will burn for trillions of years. That is not a typo, trillions. The universe is only about 13.8 billion years old right now, so this star is still in its absolute infancy. It will keep fusing hydrogen slowly and steadily, long after all the massive stars in the universe have exploded, long after our Sun has turned into a white dwarf, and long after most other stars have faded away. These lightweight red dwarfs are the ultimate survivors of the cosmos, the last stars that will still be shining when the universe enters its dark final era. Another famous lightweight star is Proxima Centauri, the closest star to our solar system, just 4.2 light-years away. Proxima Centauri is a red dwarf, with a mass of about 0.12 solar masses, still very small, but a bit heavier than Ogle Tree 122b. It is so small and dim that it cannot be seen with the naked eye from Earth, yet it is one of the most important stars in the universe for astronomers. Why? Because it has a rocky planet in its habitable zone, Proxima Centauri b, which could potentially harbor liquid water and even life. Lightweight stars, like Proxima Centauri, are the most common stars in the Milky Way. About 70% of all stars are red dwarfs. They are the unsung heroes of the galaxy, quietly burning for trillions of years and hosting most of the potentially habitable planets in the cosmos. The contrast between the heaviest and lightest stars is one of the most dramatic stories in all of astronomy. On one side, you have stars that are hundreds of times more massive than the Sun, burning bright and dying young, forging heavy elements and shaping galaxies. On the other side, you have stars that are barely bigger than planets, burning dim and living forever, hosting planets and outlasting every other object in the universe. These two extremes are not separate. They are connected by the same laws of physics, the same process of star formation, and the same cosmic story. Every star, no matter how heavy or light, starts its life the same way as a cloud of gas and dust in a stellar nursery. Gravity pulls the cloud inward, getting denser and hotter, until the core ignites fusion. The amount of material the cloud can collect determines whether it becomes a heavyweight star, a lightweight star, or a failed brown dwarf. If the cloud is huge and dense, it forms a massive star, like R136A1. If the cloud is small and sparse, it forms a tiny red dwarf, like Ogle Tree 122b. It is a simple equation, but it creates the incredible diversity of stars we see across the universe. NASA's space telescopes have been instrumental in discovering and studying these extreme stars. The Hubble Space Telescope first spotted R136A1 and measured its incredible mass, changing our understanding of stellar limits. The James Webb Space Telescope, the most powerful space telescope ever built, is now peering deeper into stellar nurseries to find even more massive stars and study the tiniest red dwarfs with unprecedented clarity. These telescopes are our eyes on the cosmos, allowing us to witness the extremes of nature and learn the secrets of how stars work. Understanding the heaviest and lightest stars also helps us answer one of the biggest questions in science: how did we get here? The heavy stars, like R136A1, create the heavy elements that make up our planet, our bodies, and everything we touch. Without these massive stars exploding as supernovae, there would be no gold, no iron, no carbon, and no life. The lightweight stars, like Proxima Centauri, are the most likely hosts for habitable planets, giving us hope that we are not alone in the universe. Every extreme star is a piece of the puzzle that explains our own existence. As we look to the future, astronomers will keep searching for even more extreme stars, stars that are heavier than R136A1, stars that are even lighter than Ogletree 122b, and stars that push the boundaries of physics even further. The universe is full of surprises, and the extremes of stellar mass are just the beginning. Every time we find a new record-breaking star, we learn a little more about the rules that govern the cosmos, and we gain a deeper sense of awe for the incredible universe we live in. The next time you look up at the night sky, remember that the stars you see are just a small fraction of the stellar family. Some are giants that burn bright and die young. Others are tiny survivors that shine for trillions of years. They are all connected, all part of the same cosmic story, and all waiting for us to learn their secrets. The heaviest and lightest stars are not just scientific curiosities. They are a reminder of the infinite wonder and diversity of the universe. A universe that is far more amazing, extreme, and beautiful than we can ever imagine. Please like, comment, share, and subscribe to the channel.